In the previous lessons, we explored topics related to the energy consumption of data centers and analyzed techniques and strategies aimed at reducing it. However, in the context of the efficiency and sustainability of digital infrastructures, it is essential to distinguish between energy consumption and environmental impact, two closely related but not equivalent concepts. Energy consumption represents the total amount of electrical energy used by a data center to power its main components, such as servers, storage, cooling systems, backup power supplies, and network infrastructure. Environmental impact, on the other hand, refers to the ecological consequences associated with this energy consumption. This includes greenhouse gas emissions, environmental pollution, the extraction of natural resources, and intensive water usage, particularly for cooling activities. A key factor in environmental impact is the energy source used. With the same energy consumption, a data center powered by renewable sources, such as wind or solar, will have a significantly lower impact compared to one that uses energy produced from fossil fuels. Furthermore, in addition to the direct emissions related to energy production, the side effects of data center operations must also be considered, such as heat generation and the resulting need for highly energy-intensive cooling systems. In summary, while energy consumption measures how much a data center uses, environmental impact measures how and to what extent that consumption negatively affects the environment. For this reason, simply reducing energy consumption is not enough. It is essential to consider the entire cycle of energy procurement and use, and to adopt a sustainable approach that involves every stage of operational management. In this lesson, we will focus precisely on these aspects, exploring the strategies that data center operators can adopt to reduce their environmental impact. The approaches we will analyze can be divided into two main categories: emission reduction strategies, which aim to directly prevent or limit the production of polluting emissions, and emission offset strategies, which act downstream, that is, after the emissions have been produced, by compensating for them through investments in environmental projects that absorb or avoid equivalent emissions. Through these approaches, data centers can make a significant contribution to achieving global sustainability goals, while at the same time maintaining efficiency, reliability, and growth capacity. The adoption of renewable energy is currently one of the most effective ways to reduce the environmental impact of data centers. Renewable sources such as solar, wind, hydroelectric, and geothermal generate energy without direct CO2 emissions and contribute to the decarbonization of the entire ICT sector. The concept of energy mix refers to the composition of the different energy sources used to power a system. In a data center, the energy mix can include renewable sources such as solar, wind, and hydroelectric, as well as non-renewable sources like coal, oil, and natural gas. The energy mix is a highly dynamic value. If the data center is powered by the national grid, the energy mix will depend on the country's energy composition, which may be more or less sustainable. Furthermore, some renewable sources, such as solar and wind, depend on weather conditions. To achieve a more sustainable energy mix, many data centers have been built in countries whose energy comes primarily from renewable sources. In addition, some data centers also include on-site renewable energy production systems, such as solar panels installed near the data centers to power their operations. If this is not possible or is not sufficient, data centers can purchase renewable energy through appropriate supply contracts. For example, Google has achieved the goal of 100% coverage with renewable energy since 2017, combining purchases of energy from wind and solar plants in different regions of the world to meet its global needs. Microsoft has invested in solar and wind plants and aims to become carbon negative by 2030. Meta has built data centers in cold and windy regions, such as Sweden, to take advantage of the natural climate and the abundance of clean energy sources. Another strategy to reduce the environmental impact of data centers is to use sustainable backup systems. Traditionally, data centers use diesel generators as backup for power production in case of blackouts. In this way, they ensure service continuity and limit potential damage. More modern solutions replace diesel generators with lithium-ion batteries or generators powered by renewable sources, reducing the emissions associated with energy backup. Another aspect to consider in the sustainability of data centers concerns the circular economy and the management of electronic waste. Hardware components generate emissions not only during their operation, but also in the phases of production, transportation, and disposal. Moreover, rapid obsolescence and the relatively short life cycle of many devices contribute to the accumulation of waste and the intensive use of natural resources. To reduce this impact, it is essential to adopt design and management strategies focused on circularity, which include designing more durable and easily repairable devices, as well as implementing recycling and reuse programs that allow for the recovery of valuable materials from discarded devices. A concrete example is the global program launched by Dell Technologies, which offers solutions for the collection, recycling, and reuse of obsolete hardware. The recovered materials are reintegrated into the company's production cycles, reducing the need for raw materials and contributing to a more sustainable production model. Given the dynamic nature of renewable energy sources and the high energy consumption of data centers, powering a data center exclusively with renewable energy is very complicated. To achieve carbon neutrality, data centers can resort to mechanisms that offset the emissions they produce. Carbon offsetting is a mechanism that allows an organization to balance its own emissions by purchasing credits that represent CO2 reductions achieved elsewhere. A data center that is unable to cover 100% of its consumption with renewable energy can purchase credits to offset its remaining emissions. One credit corresponds to 1 ton of CO2 avoided or removed from the atmosphere. These credits are certified by third-party organizations that verify the actual emission reductions associated with the project. Offset projects can include reforestation or protection of existing forests, renewable energy projects in developing countries, carbon capture and storage technologies, and improvements in energy efficiency within local communities. Offset mechanisms make it possible to address emissions that cannot be directly eliminated in a quick and flexible way. However, they have several critical aspects that need to be considered. The first issue is the risk of greenwashing. Some companies use carbon offsetting as an excuse not to actually reduce their own emissions, but instead to compensate for their activities by purchasing carbon credits. In the long term, this strategy is not sustainable. Offsetting should be a complement to directly reducing emissions, not an alternative. Another issue is the lack of uniform standards and reliable verification mechanisms to assess the effectiveness and integrity of offset projects. It is not always possible to determine with certainty whether a project has actually generated the claimed environmental benefit. Moreover, the promised benefits may be temporary or reversible, as in the case of reforestation projects that are subject to future fires or deforestation. For these reasons, it is essential that companies adopt a transparent and responsible approach to emissions offsetting, choosing certified and verifiable projects and integrating offsetting activities within a broader climate strategy. Renewable energy and carbon offset mechanisms are key tools for reducing the environmental impact of data centers. However, their use must be part of a broad and coherent strategy that prioritizes direct emissions reduction and ongoing operational efficiency.